Okay, so in the previous video, we talked about what sampling distribution is. And in this video, we introduce two important definitions of sampling distribution. One is mean and one is standard error. Okay, so these two definitions are very important basics to solve real-world problems in sampling distribution. So the first definition is what is the mean of sample means? Okay, so mean of sample means is the mean of all possible sample means, and is always equal to the population mean. So as you already know, the population mean is represented by mu, and here the mean of sample mean is represented by mu of x bar, simply because x bar represent sample means. So if you look at the curve of population distribution, and then if you look at sampling distribution of the corresponding population distribution, you can see that their centers are the same, which means the mean of population is always equal to the mean of the sample means. So we have seen the mean of sample means in the previous video, where we have calculated all the 16 sample means, x bar, and then from the 16 sample means, we can calculate the average of the 16 numbers, which is 21 years old, and that gives us the mu of x bar, which is the mean of sample means. Okay, and the second definition of sampling distribution is standard error of sample means. Standard error of sample means is the standard deviation of all possible sample means, and it's always smaller than the population standard deviation. So you know that the population standard deviation is represented by sigma, and the sample size is represented by the little n. And here, the new definition, which is standard error of sample means, is represented by sigma of x bar, because x bar represents the sample means, so sigma of x bar represents the standard error of sample means. Here you can see that if n, little n, increases, then the sigma of x bar is gonna decrease. And if the sample size little n decrease, and then the sigma of x bar, which is the standard error of sample mean, would increase. So if you look at the curve, if you have a smaller sample size, then the distribution of the sample means would be more spread out with a higher variability. If you have a larger sample size, then the sampling distribution would be more concentrated with less variability, or smaller standard error of sample means. Okay, so sampling distribution has two possible scenarios. One is possible scenario is population is normal, and the other scenario is population is not normal. But no matter the population distribution is normally distributed or not normally distributed, the mean of sample mean and the standard error of sample means, they always follow these two formulas, no matter the population is normal or not. Okay, so the difference is if population is normally distributed, then the sampling distribution of sample means is always normally distributed regardless of the sample size. However, if population is not normally distributed, then the sampling distribution is not necessarily normally distributed, and is only normally distributed with a specific number of the sample size, and we'll discuss that later. Okay, so now let's take a look at a real-world problem, which is an example in quality control. And in this example, we want to show if x value is given, how can we determine the probability? Okay, so the problem is like this. The packaging equipment that is filling 3 68-gram boxes of cereal is set so that the amount of cereal follows a normal distribution with a mean of mu equals 368 grams. From the past experience, the population standard deviation for this filling process is sigma equals 15 grams. And you want to test whether this is true or not. Question A, what is the probability that an individual box will contain less than 365 grams of cereal. So this question can be answered easily with your previous knowledge from previous chapter in normal distribution. And this has nothing to do with today's class. Okay, so if you look at the solution, you should be pretty. So the first step is always to list out the parameters. So here the parameters include the population mean, which is 368 grams, population standard deviation, which is 15 grams, and the sample mean, which is X bar, which is 365, which is the X value that we have used before. Okay, so the second step is to calculate the Z value. To get the Z value, we simply plug in the three numbers to the formula of the Z value and then get the Z value, which is negative 0.2. And once you have the Z value, you'll look up the Z table and find out the corresponding probability p-value corresponding to the Z value, which gives you the 42%. Okay, so that's question A, which used knowledge from the previous chapter. And now let's take a look at question B. Question B is, suppose a random sample of size 25 is selected. What is the probability that the sample of 25 boxes will have a mean below 365 grams? Okay, so this is based on sampling distribution because first, we have a sample size of 25. Second, we're looking for the probability the probability that the sample mean is below a threshold. Okay, so now let's see how do we solve for this problem. In order to solve question B, we first of all need to know what is the formula of Z value for sampling distribution. So as you can see that the Z value formula is slightly different from the previous Z value of normal distribution. In normal distribution, we have X minus mu divided by sigma. And here, X is replaced by X bar. Mu is replaced by mu of X bar. And sigma is replaced by sigma of X bar. And X bar represents the sample means. So if we plug in the formula from here, if we replace mu of X bar with mu, and if we replace sigma of X bar with sigma divided by square root of little n, then we will come up with this formula. And this is a formula we're going to use to solve our sampling distribution problems. Okay, so let's take a look at the solution for question B. For question B, the first step is still to list out the parameters: the population mean, population standard deviation, sample size, and X bar, sample means. To calculate the Z value, you simply use a formula from the previous slide, plug in all the numbers, and get the Z value of -1. And the third step is to look at the Z table and figure out what is the probability p-value corresponding to the Z value of -1. So if you compare the difference between question A and question B, and you can see that the only difference between the solutions is the square root of 25. Okay, so in the previous question A, you do not have to divide it by the square root of 25. In question B, the sigma, which is the standard deviation of population, has to be divided by the square root of 25, simply because the standard error of sampling means is equal to the population standard deviation divided by square root of sample size. Okay, so that's the only difference between sampling distribution of the mean and population distribution of the mean. Okay. And the second application of sampling distribution is to calculate the interval or the X values for the given probability. So we have already solved this kind of problem as well before in normal probability in the previous chapter. So let's use the same example in quality control as well. And the question becomes, what is interval symmetrically distributed around the population mean that will include 95% of the sample means? Okay, so in order to figure out what the x value is corresponding to a given probability or a given z value, you simply need a formula to do that. And here is a formula. So if you remember the formula to calculate x values given z values, you probably remember it is x value equals mu plus z times sigma. So again, the only difference here is the sigma has to be divided by the square root of sample size little n. So that's the only difference as well. So it's pretty easy to remember. So just use a formula for the normal distribution, and the only difference is to pay attention on the standard error of sample means by dividing the square root of sample size n. Okay, so now let's solve the problem. Interval. The question is, what is a symmetrically distributed interval around the population mean that would include 95% of sample means? Because interval contains 95%, then the rest of it, which is outside of interval, would be the complement of 95%, which is 1 minus 0.95, which is 5%. And because interval is symmetric, that means half of 5% is on the left and half of 5% is on the right. Or 2.5% will be above the upper limit and 2.5% will be below the lower limit. And from the z-table, the z-score with 2.5 of lower level probability is negative 1.96. And the z-score with the 2.5% right tail probability is 1.96. Okay, so now let's use a formula that we just learned to calculate the lower limit and upper limit, or the left boundary and the right boundary of this 95% interval. So what you simply need to do is to plug in the parameters of population mean, the population standard deviation, and the sample size. And the difference between the lower limit and upper limit is simply the z values. One z value is negative 1.96 and the other z value is 1.96, and then you're going to get two boundaries or two limits of the intervals. Okay, so what we have been talking so far is all based on the assumption that the population is normal. But the second scenario is the population is not normally distributed. And what shall we do with that case? In this case, we can apply the central limit theorem. So the central limit theorem tells us that even if the population is not normally distributed, the sample means will still be approximately normally distributed as long as the sample size is large enough. And the similar distribution still follows the two formulas. Okay, so if you take a look at this curve, so this blue line represents the population distribution, and as you can see, the population distribution is not normally distributed because it is right skewed, and you can see that a longer right tail right here. However, if you take the sampling distribution from this population distribution, and as the sample size gets large enough, then the sampling distribution of this population distribution will look like a normal distribution. That means, regardless of how the shape of the population is, the sampling distribution of the sample mean can always become almost normal if your sample size gets large enough. Okay, so now we can see that sampling distribution from this population distribution, which is not normal, the sampling distribution can still become a normal distribution if the sample size gets large enough. Okay, so now the question is how large is large enough? For most population distributions, the threshold is a sample size of 30. If the sample size is greater than 30, then your sampling distribution would be nearly normal. But if your population is already fairly symmetric, then you only need to have a sample size that is greater than 15 in order to get a normal sampling distribution. And if your population distribution is already a normal distribution, then the sampling distribution is always normally distributed regardless of the sample size. Okay, so I'm going to skip this example because the only difference between a normal population and a not normal population is simply to make sure that your sample size is greater than 30. As long as your sample size is greater than 30, then all the steps are the same.